Apply a linear transformation to a coordinate space, and the geometry warps. Grid lines shear, angles compress, and the structure twists into a new configuration. To rigorously analyze this behavior, we rely on the formal algebra established by Kenneth Hoffman and Ray Kunze, whose MIT curriculum defined undergraduate linear algebra. When a matrix multiplies a standard vector, it is typically knocked off its original span. It changes length and points in a new direction. But there are exceptions. Some vectors refuse to rotate. They only stretch or shrink in place, anchored to their original line. These unchanged vectors act as the foundational axes of the transformation. They define the specific lines along which the linear operator behaves as simple scaling, rather than rotation or shear. To find these axes, we have to translate this geometric observation into the rigorous notation used by Hoffman and Kunze. The stretching behavior is captured by this equation. On the left, we apply the transformation t to our vector v. On the right, the result is the same vector v multiplied by a single scalar, lambda. The v component is our characteristic vector, the specific direction that refuses to change its angle during the transformation. The lambda is the characteristic value. It is the exact scalar multiplier that determines how much the vector stretches, shrinks, or reverses along that fixed line. Calculating these lambda values reveals the exact factor by which the entire coordinate space is scaled along these invariant foundational lines. The problem is finding a systematic way to calculate these lambdas for complex, multidimensional matrices. We start by moving all terms to one side of the equation to isolate 0. The transformation t is represented by the matrix A, giving us A times V minus lambda times V equals 0. Since we cannot subtract a single scalar from a matrix, we multiply lambda by the identity matrix, I. Now we can factor out the vector v, leaving us with the matrix A minus lambda I multiplied by v equals 0. For the vector v to be a non-zero direction, this new shifted matrix, A minus lambda I, must be singular. It must squash the coordinate space down to a lower dimension. A matrix is singular if its determinant equals 0. Setting the determinant of A minus lambda I to 0 creates a polynomial equation where the variable is lambda. Hoffman and Kunze formalize this in Theorem 1. The characteristic values of a matrix are precisely the roots of its characteristic polynomial. This determinant equation identifies the specific scalars where a matrix loses its full rank properties, allowing us to locate these invariant axes through algebraic roots. However, the existence of a characteristic polynomial does not always guarantee the existence of a corresponding characteristic vector. Take Hoffman and Kunze's example 1, a 2x2 matrix rotating a coordinate plane by 90 degrees. Its characteristic polynomial results in lambda squared plus 1 equals 0. This requires finding a lambda where lambda squared equals -1. In the field of real numbers, this polynomial has no roots. But if we expand our field to the complex plane, we find two characteristic values, I and -I. Because a 90-degree rotation moves every vector in real space off its original axis, the math requires a complex field to find a solution, showing how the scalar field dictates the existence of these vectors. One primary application of finding these values is diagonalizability, the process of simplifying a matrix to its core scaling factors. Theorem 2 states a matrix is diagonalizable only if the number of times a root appears algebraically matches the geometric dimension of its null space. In example 2, the characteristic polynomial has roots of 1 and 2. Because the factor lambda minus q is squared, the algebraic multiplicity of the root 2 is 2. We find the characteristic vectors for this root by plugging the value 2 back into the shifted matrix equation, A minus 2i. This results in a matrix of rank 2. In a three-dimensional space, that leaves only a one-dimensional null space. Even though the algebraic root appeared twice, it only generated a single line of characteristic vectors. Because the geometric dimension fails to match the algebraic multiplicity, this matrix is defective and cannot be diagonalized. Example 3 uses a different matrix that produces the exact same characteristic polynomial, with the root 2 again repeated twice. Plugging 2 into this specific A minus 2i matrix yields a different result. The row reduction shows that this matrix only has a rank of 1. A rank 1 matrix in three-dimensional space guarantees a two-dimensional null space. The algebraic root and the geometric dimension now match perfectly at 2. This matrix satisfies the requirements of Theorem 2. Because these dimensions match, the matrix can be diagonalized, allowing the transformation to be represented by simple scalar multiplication along its characteristic vectors. By moving through these examples, we've established a complete analytical framework for linear operators. First, characteristic values isolate the specific lines where a complex transformation acts as simple scaling. Second, the characteristic polynomial extracts these values from the matrix. Finally, comparing polynomial roots to null space dimensions verifies a matrice's structural integrity through diagonalizability. This rigorous approach to geometric problems is a central theme in seminal texts like Hoffman and Kunze, forming the basis for advanced linear algebra. If you appreciate rigorous breakdowns of mathematical concepts, please like and subscribe for more in-depth research.